May 17th, 1944. 22,000 feet over Brandenburg, Germany. Oberleutnant Klaus Hartmann tightened his grip on the stick of his Messerschmitt Bf 109G as he spotted the lone P-51 Mustang below. He'd faced these American fighters a dozen times before. He knew their capabilities by heart. Maximum speed, 437 miles per hour at altitude. Climb rate, predictable. Energy retention, within calculated parameters. He rolled into his attack, confidence born from experience and training. The Mustang pilot saw him coming and pushed his throttle forward. Hartmann expected the standard evasion, a diving turn perhaps, using the Mustang's superior roll rate. What happened next made no sense. The Mustang didn't just accelerate, it surged. The American fighter pulled away as if Hartmann's 109 was nailed to the sky. His airspeed indicator showed he was at maximum performance. The Mustang was simply faster. Impossibly faster. Das kann nicht, he muttered into his radio. This cannot be, but it was. What Hartmann didn't know, and what none of the Luftwaffe knew, was that the Americans had just changed the rules of aerial combat. Not with a new aircraft, but with a purple liquid pumped into the fuel tanks. By late spring 1944, Luftwaffe intelligence officers were growing concerned. Pilot reports from the Western Front were piling up on their desks, each one describing the same impossible phenomenon. American P-51 Mustangs were performing beyond their documented specifications. Oberfeldwebel Heinrich Müller, a veteran with 47 kills, reported encountering a Mustang that outran his Focke-Wulf 190 in level flight by what he estimated was 50 miles per hour. Hauptmann Werner Schmidt claimed a Mustang had climbed away from him at rates that exceeded the aircraft's known performance envelope. Lieutenant Franz Weber swore he'd engaged a Mustang that accelerated in a shallow dive faster than anything he'd ever seen. The intelligence officers reviewed the reports with growing skepticism. These were experienced pilots, yes, but they were also exhausted men flying against overwhelming odds. Combat stress, they concluded, fatigue-induced exaggeration, the fog of war playing tricks on tired minds. The numbers in the reports simply didn't match reality. The P-51B and D models had a documented maximum speed of 437 miles per hour at 25,000 feet. German test pilots had flown captured Mustangs. They knew exactly what the aircraft could do. Except now, apparently, they didn't. What the Luftwaffe intelligence officers dismissed as pilot error was actually pilots reporting exactly what they saw. Mustangs flying at speeds approaching 450 miles per hour. Mustangs with climb rates that defied their performance charts. Mustangs that could run down any German fighter in service. The reports weren't wrong, the Americans had changed the equation. The answer wasn't visible in the air, it was invisible, flowing through fuel lines and burning in combustion chambers. At Wright Field in Dayton, Ohio, test pilots had been evaluating something extraordinary since early 1944. A new aviation gasoline, dyed purple for easy identification, designated simply as Grade 150 fuel. The test results were remarkable. A P-51B Mustang running on standard 130 grade fuel reached 437 miles per hour at 25,000 feet, exactly as the performance charts predicted. The same aircraft, flown by the same pilot, at the same altitude, running on 150 grade fuel, exceeded 448 miles per hour, 11 miles per hour faster. That might not sound revolutionary, but in aerial combat, where the difference between life and death could be measured in seconds and feet, 11 miles per hour was the difference between catching an enemy fighter and watching it escape, between outrunning an attacker and being shot down, and speed was only part of the advantage. The Packard Merlin V1650-7 engine that powered the P-51D generated 1,490 horsepower at military power settings on 130 grade fuel. Running on 150 grade fuel at war emergency power, that same engine produced 1,720 horsepower. An increase of 230 horsepower, the equivalent of bolting an entirely new engine into the aircraft, achieved simply by changing what flowed through the fuel tanks. Climb rates improved by several hundred feet per minute. Acceleration in all flight regimes increased dramatically. Most importantly, these improvements required zero modifications to the aircraft itself. No new propellers, no engine upgrades, no aerodynamic changes, just fuel. Purple-dyed, high-performance aviation gasoline that transformed good fighters into exceptional ones. The tactical implications were devastating for the Luftwaffe. Germany's frontline fighter in early 1944, the Messerschmitt Bf-109G, had a maximum speed of 400 miles per hour at altitude. The Focke-Wulf 190A, considered by many German pilots to be superior, could reach 408 miles per hour under optimal conditions. Against Mustangs running 130 grade fuel at 437 miles per hour, German pilots could still engage on carefully chosen terms. They could use altitude advantage, tactical positioning, and superior numbers to force combat. If things went badly, they had a reasonable chance of disengaging and escaping. Against Mustangs running 150 grade fuel at 448 plus miles per hour, the mathematics of aerial combat shifted irrevocably. German fighters couldn't catch what they couldn't match. American pilots could choose when to fight and when to disengage. They could pursue fleeing German fighters with near impunity. They could defend bomber formations aggressively, knowing they had the speed to chase down attackers. For German pilots, the tactical options narrowed to a grim few. Engage and accept the performance disadvantage, refuse combat entirely, or attempt massed attacks hoping numbers would overcome capability. No amount of pilot skill, tactical cunning, or operational experience could compensate for being fundamentally, measurably slower. And the Luftwaffe didn't even know why it was happening. To understand what the Americans had achieved, you need to understand what octane actually means. Octane rating measures a fuel's resistance to detonation. Inside an aircraft engine, the piston compresses the air-fuel mixture during the compression stroke. As the mixture compresses, temperature and pressure skyrocket. If the fuel ignites spontaneously before the spark plug fires, the result is detonation, an uncontrolled explosion rather than a controlled burn. Detonation creates shock waves that can crack pistons, damage cylinder heads, and destroy engines in seconds. Higher octane ratings mean the fuel can withstand more compression without detonating. More compression means more power from each combustion cycle. More power means faster aircraft. The science was straightforward. The engineering was not. By definition, octane ratings cannot exceed 100, because 100 octane means detonation resistance equivalent to pure iso-octane, the reference standard. So how could fuel be rated at 150? The answer: performance numbers. A fuel with a performance number of 150 doesn't have an octane rating of 150. That's chemically impossible. Instead, it means the fuel can withstand 50% more compression than pure iso-octane before detonating. Creating such a fuel required adding anti-knock compounds, primarily tetraethyl lead, and carefully blending aromatic hydrocarbons like toluene and xylene with base gasoline. British chemists at the Royal Aircraft Establishment and American researchers at Wright Field spent years testing thousands of blends, seeking the optimal combination of anti-knock performance, energy content, and manufacturing practicality. By early 1943, they had succeeded. The path to 150-grade fuel began years before, driven by the brutal realities of aerial combat. In 1940, when war was already consuming Europe, American aviation fuel production centered on 87 octane gasoline, adequate for commercial aviation and training aircraft, woefully insufficient for high-performance combat. The British, desperate for any advantage against superior German numbers, worked with American oil companies to develop 100-octane fuel. It arrived just in time for the Battle of Britain in summer 1940. The results were immediate and dramatic. British Spitfires and Hurricanes, using 100-octane fuel, suddenly gained 30 to 40 miles per hour at altitude. Climb rates increased by 500 to 1,000 feet per minute. German pilots flying on 91-octane fuel, who had enjoyed performance advantages, suddenly found themselves on even terms. The lesson was clear. Fuel chemistry could change the outcome of air battles. By 1943, the Allies had developed 130-grade fuel, which became the backbone of Allied air power. It powered Merlin engines in Spitfires and Mustangs, Allison engines in P-38 Lightnings, and massive Pratt & Whitney radials in P-47 Thunderbolts. Production scaled rapidly under the direction of General James Doolittle, who had spent the 1930s advocating for high-octane fuel development. 17 Allied refineries were producing high-octane aviation gasoline using the catalytic cracking process perfected by French immigrant engineer Eugene Houdry. American refineries alone produced millions of gallons monthly, enough to fuel the massive bomber offensive against Germany and the growing fighter forces protecting those bombers. German fuel production, by contrast, remained bottlenecked by their reliance on synthetic fuel derived from coal. While Allied chemists pushed toward 150-grade fuel, Germany struggled with fundamental resource constraints. The Burgius process that converted German coal into aviation gasoline was technically sound but painfully slow and resource-intensive. Even at peak production, Germany could produce only a fraction of the high-octane fuel flowing from American refineries. Most German fighters flew on B4 fuel, rated at approximately 91 octane. Their premium C3 fuel, used primarily in BMW 801-powered Focke-Wulf 190s and select Messerschmitt variants, was roughly equivalent to Allied 130-grade fuel, but available in desperately limited quantities. By 1944, perhaps two-thirds of German aviation fuel production was C3 grade. This sounds encouraging until you realize it still represented only a tiny fraction of Allied production. The numbers tell the story. Between May 1944 and April 1945, Allied production of 150-grade fuel alone likely exceeded 200 million gallons. The 8th Air Force, just one component of Allied air power, consumed over 53 million gallons of 150-grade fuel during this period. Germany simply could not compete at this scale. Their synthetic fuel plants couldn't match Allied output. Their chemistry couldn't match Allied performance. And soon Allied bombers would target those fuel plants directly, transforming a disadvantage into a crisis. In May 1944, as Allied forces prepared for the invasion of Normandy, the first operational deliveries of 150-grade fuel arrived in England. The timing was deliberate. The 8th Air Force, conducting daylight strategic bombing raids deep into Germany, was suffering unsustainable losses. Despite the arrival of long-range P-51 Mustangs in December 1943, German fighter forces were still inflicting heavy casualties on American bomber formations. What American planners needed was not just an escort fighter with range, but an escort fighter so fast that German interceptors could not easily escape or refuse combat on unfavorable terms. Distribution was carefully controlled. Not every fighter group received the new fuel immediately. The 8th Air Force began with select squadrons, both to manage supply logistics and to evaluate combat performance under operational conditions. Purple-dyed fuel trucks rolled onto English airfields, their cargo clearly marked to prevent accidental mixing with standard grades. Ground crews received briefings on handling procedures. The high tetraethyl lead content required protective equipment and careful protocols. The British Royal Air Force, which had pioneered much of the early testing, also began equipping fighter squadrons with the new fuel. Priority went to units tasked with high-speed interception missions, particularly those hunting German V-1 flying bombs that began terrorizing London in June 1944. The V-1 flew at approximately 400 miles per hour at low altitude. Intercepting these weapons required fighters capable of matching or exceeding that speed, where air density reduced all aircraft performance. Hawker Tempests could barely catch them. Spitfire 14s were marginal. Mustangs running standard fuel struggled. Mustangs running 150 grade fuel had sufficient speed margin to intercept reliably. On June 18, 1944, Major Robert E. Turner of the 356th Fighter Squadron destroyed a V-1 flying bomb using a technique that became legendary. He positioned his P-51's wingtip within 6 inches of the V-1's wing surface, then used the airflow disruption to roll the flying bomb off course, sending it crashing into unpopulated countryside. This maneuver required exceptional speed and precision. Turner had both, courtesy of purple-dyed gasoline burning in his Merlin engine. The first widespread combat use of 150-grade fuel by American P-51 pilots occurred in June 1944, coinciding with the Normandy invasion. Fighter groups of the 8th Air Force, tasked with achieving air superiority over the invasion beaches, flew combat air patrols and bomber escorts using the new fuel. The results were immediate. German fighter pilots began reporting encounters with Mustangs that performed beyond anything they had previously experienced. Luftwaffe intelligence officers collected reports describing American fighters that could not be caught in any flight regime, that could accelerate away from German interceptors with ease, that seemed to have power reserves defying all explanation. These reports landed on desks in Berlin with increasing frequency through June and July. Intelligence officers reviewed them with the same skepticism they had shown earlier reports. The pilots, they reasoned, were exhausted, outnumbered, facing mounting losses and deteriorating tactical situations. Their reports of superior American fighter performance were surely the result of stress and fatigue rather than actual performance increases. This assessment was catastrophically wrong. What German intelligence officers dismissed as psychological breakdown was actually accurate combat reporting. American Mustangs were performing beyond documented specifications. German pilots weren't cracking under pressure. They were encountering aircraft whose performance had been chemically enhanced beyond design parameters. The truth would remain hidden until after the war. Günter Rahl, a Luftwaffe ace with 275 victories, most achieved on the Eastern Front, flew combat missions against American fighters over Germany in 1944. In interviews conducted decades later, during the 1970s and 1980s, Rahl spoke candidly about his shock at encountering late-war Mustangs. He described performance that exceeded anything he had seen in 4 years of combat. Speed that defied explanation. Climb rates that shouldn't have been possible. After the war, Rahl test flew captured American fighters, including P-51s, P-47s, and P-38s. The Mustang particularly impressed him with its speed, climb capability, and high-altitude performance. But what Rahl and other German pilots didn't realize during combat was that they were facing aircraft operating at power settings the original engineers had never envisioned, running boost pressures that should have destroyed engines. achieving performance that existed only because of chemistry developed in distant laboratories. They were fighting airframes they recognized, powered by fuel they couldn't match, and they were losing because of it. The purple liquid flowing into P-51 fuel tanks represented far more than chemistry. It represented an industrial supply chain that Germany could not replicate. Every gallon of 150-grade fuel required refining infrastructure operating at scales that defied imagination. Chemical additives, including highly toxic tetraethyl lead, had to be produced, transported, and blended with precision. Quality control testing ensured every batch met strict performance standards. The fuel then travelled across the Atlantic, thousands of miles by tanker ship, to arrive at British ports. From there, it moved to secure storage facilities scattered across England. Distribution networks delivered it to dozens of airfields, housing American and British fighter squadrons. Ground crews pumped it into aircraft, mission after mission, day after day. Between May 1944 and April 1945, the 8th Air Force alone consumed over 53 million gallons of 150-grade fuel. Total Allied production across all refineries likely exceeded 200 million gallons during operational use. This wasn't just fuel production. This was industrial warfare operating at a scale that Germany, for all its engineering prowess, simply could not match. But 150-grade fuel came with costs. The high tetraethyl lead content that provided exceptional anti-knock performance also created significant challenges. Lead was highly toxic. Ground crews handling the fuel required protective equipment. Spills had to be cleaned immediately to prevent poisoning. Inside the engines, the high lead content left deposits on spark plugs, valves, and cylinder walls. Spark plugs fouled more frequently. Cylinder wear accelerated. Engine components that normally lasted hundreds of hours showed wear patterns after significantly shorter periods. American maintenance procedures adapted rapidly. Spark plug replacement intervals were shortened dramatically. Cylinder inspections became more frequent. Engine overhaul schedules were adjusted to account for the increased wear. Fighter groups using 150-grade fuel experienced maintenance burdens that would have been unacceptable in peacetime. In wartime, facing an enemy that had to be defeated, the trade-off was obvious. Performance gains were worth the increased maintenance costs. German fighters limited by 91 octane fuel and scarce C3 supplies couldn't compete with Mustangs running 150 grade, regardless of how much maintenance those Mustangs required. The choice wasn't between clean engines and dirty engines. It was between air superiority and defeat. American ground crews worked longer hours, replaced more parts, and accepted the burden because the alternative was unthinkable. For pilots, the transition to 150-grade fuel required learning new operating procedures. Manifold pressure limits were raised substantially. Pilots could now push their engines to boost levels that would have destroyed earlier power plants. But this capability came with risks. Overboosting, particularly at low altitudes where air density was highest, could still cause catastrophic engine failure. Pilots had to learn the limits of their new capability and respect those limits even in combat. The most critical challenge was fuel management. The 150-grade fuel provided dramatically more power, but running at maximum boost consumed fuel at rates that pushed the Mustang's range to its absolute limits. Escort missions to Berlin and back already demanded careful fuel management. Using 150-grade fuel's full capability meant even more careful planning. Pilots had to know when to use war emergency power, typically only during combat engagement, and when to throttle back to cruise settings for maximum range efficiency. Training programs incorporated these new procedures. Pilots received detailed briefings on the fuel's properties, updated engine operating limits, and tactical guidelines for when and how to use maximum power settings. The learning curve was steep but manageable. American pilot training programs, which typically gave pilots several hundred hours of flight time before combat assignment, had time to incorporate the new procedures. German pilots, by contrast, were reaching operational units with minimal experience. By late 1944, fuel shortages had cut training time so severely that some German pilots entered combat with less than 50 hours of total flight time. They faced American pilots who not only flew superior aircraft powered by superior fuel, but who also had the training time to master those advantages fully. The contrast between American and German industrial capacity in 1944 was stark and decisive. American factories produced bombers by the thousands and fighters by the tens of thousands. Shipyards launched Liberty ships faster than Germany could sink them. Oil refineries produced aviation gasoline in quantities that exceeded Germany's total fuel production across all grades combined. This advantage stemmed from decades of industrial development, vast natural resources, and a homeland protected from strategic bombing. Millions of American women had entered the workforce, taking factory jobs that kept production lines running around the clock. Germany possessed skilled engineers, experienced workers, and sophisticated manufacturing capability, but they couldn't overcome the fundamental arithmetic of total war against opponents who could outproduce them in every category that mattered. The numbers tell a story of transformation. Between January and May 1944, before the widespread introduction of 150-grade fuel, American bomber formations suffered loss rates of approximately 3 to 6% per mission. These were sustainable losses, barely, but they represented hundreds of aircraft and thousands of aircrew killed, wounded, or captured. Between June and December 1944, after 150-grade fuel reached operational squadrons, loss rates dropped to under 2% per mission. Fighter victories surged. American P-51 groups across the 8th, 9th, and 15th Air Forces claimed approximately 4,950 German aircraft destroyed in air-to-air combat between late 1943 and May 1945. A significant portion of those victories came after June 1944, when Mustangs powered by 150-grade fuel dominated the skies over Europe. An additional 4,131 German aircraft were destroyed on the ground, caught at airfields by fighters that could penetrate deep into Germany, strafe with impunity, and return home with fuel to spare. These numbers represented more than aircraft destroyed. They represented pilots killed, experience lost, and German industrial capacity wasted building replacements that were themselves destroyed before achieving any strategic effect. By March 1945, virtually every P-51 unit in Europe was running 150-grade fuel. Combat reports from this period show results that were overwhelmingly one-sided. German fighters rarely challenged Allied formations effectively. When they did fight, they usually suffered devastating losses. By April 1945, American bomber missions over Germany often encountered zero aerial opposition. The Luftwaffe was finished. The destruction of the Luftwaffe resulted from multiple converging factors, but fuel played a central role in the final collapse. Already outnumbered and outmatched in pilot training, German fighter forces faced an enemy that could now outperform them in every flight regime. Tactical options that had once existed, even if barely, simply vanished. German pilots flew knowing that every sortie might be their last, not because they might be shot down, but because there might not be fuel for another mission. Training for replacement pilots had been cut to near zero. New pilots reached operational units with flight experience measured in dozens of hours rather than hundreds. Meanwhile, Allied bombing of German synthetic fuel plants, particularly the devastating raids on Leuna and other major facilities in May and June 1944 transformed a disadvantage into a crisis. Production that had barely been adequate became completely insufficient. The Luftwaffe began rationing fuel strictly. Fighter units received priority over all other aviation units, but even frontline fighters operated under constraints that crippled effectiveness. By spring 1945, as Allied armies overran Germany from east and west, the Luftwaffe had ceased to exist as a coherent fighting force. A few elite units still flew, often with barely enough fuel for a single sortie. Jet fighters like the Me-262 represented a technological leap forward, but they arrived too late, in too few numbers, and were handicapped by fuel shortages and the absence of experienced pilots. On June 6, 1944, D-Day, only 2 Luftwaffe aircraft appeared over the Normandy invasion beaches. Germany still possessed thousands of fighters scattered across occupied Europe. But they lacked the fuel to fly them, the pilots to fly them effectively, and the tactical flexibility to deploy them where needed. The contrast between Allied and German operational realities by late 1944 was absolute. Allied fighters flew multiple combat missions daily, limited only by pilot fatigue and aircraft maintenance schedules. They maintained standing patrols over critical areas. They reacted aggressively to any threat. Pilots used full power whenever tactically necessary, confident that adequate fuel reserves existed for the return flight. This operational confidence bred tactical aggression. American pilots knew their aircraft were faster, their fuel was plentiful, and their support infrastructure was robust. They pressed attacks. They pursued fleeing enemies. They dominated the air not just through numbers, but through the psychological advantage of material superiority. German pilots, by contrast, flew under constant fuel constraints. Burning too much fuel during combat meant potentially running out before reaching base. Many German pilots broke off engagements not because they were losing tactically, but because fuel gauges showed dangerous levels. They had to pick their moments carefully, conserve fuel rigidly, and often refuse combat simply because they couldn't afford the fuel consumption that aggressive maneuvering required. It wasn't just about who had better aircraft or better pilots. It was about who could sustain operations without the constant fear that the fuel trucks wouldn't come tomorrow. When historians analyze the Allied victory in the air war over Europe, they point to multiple decisive factors. The P-51 Mustangs' exceptional range, American pilot training programs that produced skilled aviators by the thousands, overwhelming numerical superiority, strategic bombing that crippled German industrial capacity. All of these factors mattered. All of them contributed to the outcome. But 150-grade fuel represented something different. It represented the margin between a hard-fought victory and an overwhelming one. The difference between air superiority grudgingly won and air supremacy absolutely achieved. Those 11 extra miles per hour at altitude. That additional 230 horsepower at war emergency power. Those improved climb rates and acceleration curves. These advantages didn't just make American fighters slightly better, they made them categorically superior in ways that German pilots couldn't overcome through skill, tactics, or courage. When a P-51 Mustang reached 448 miles per hour at 25,000 feet, that number represented more than velocity. It represented technological superiority, industrial capacity, chemical engineering expertise, and the accumulated advantages of nations that could innovate faster than their enemies could respond. German military planners in 1943 and early 1944 based their defensive strategies on careful calculations. They knew American fighters would escort bomber formations. They knew the P-51 Mustang had exceptional range. They understood that Allied numerical superiority would eventually become overwhelming. Their plans accounted for these realities. What they didn't account for, what they couldn't account for, was that American fighters would suddenly perform beyond the parameters that German intelligence had documented. When you capture an enemy aircraft and test it thoroughly, you assume you understand its capabilities. When your pilots encounter that same aircraft type dozens or hundreds of times, you assume their reports establish reliable performance baselines. German planners made those reasonable assumptions, and those assumptions were rendered obsolete by chemistry developed in laboratories thousands of miles from any battlefield. The fuel flowing through Allied supply chains represented an advantage that German planners never saw coming. By the time they understood what was happening, when captured samples confirmed that American fuel had performance characteristics beyond anything German synthetic plants could produce, it was too late. The infrastructure gap couldn't be closed. The chemistry couldn't be replicated at scale. The industrial capacity didn't exist. The story of 150-grade fuel illuminates a fundamental truth about the Second World War. Victory didn't belong to the side with the bravest soldiers or the most brilliant generals. It belonged to the side that could mobilize industrial capacity on scales that transformed warfare itself. The side that could produce not just adequate equipment, but superior equipment in overwhelming quantities. The side that could innovate not just in aircraft design or tactics, but in petroleum chemistry and logistics networks. The side that could deliver hundreds of millions of gallons of specialized fuel to forward airfields and sustain that delivery month after month. German soldiers fought with remarkable courage and skill. German engineers designed sophisticated weapons. German pilots demonstrated extraordinary bravery against impossible odds. But courage and skill couldn't overcome the fundamental arithmetic of total war against opponents who could outproduce, out-innovate, and outlast them in every category that determined modern warfare's outcome. The petroleum chemists and engineers who developed 150-grade fuel never flew combat missions over Germany. They never faced anti-aircraft fire or enemy fighters. Their names don't appear in lists of war heroes or Medal of Honor recipients. But their work, conducted in refineries and laboratories far from any front line, helped decide who would control the skies over Europe in 1944 and 1945. Every time a P-51 pilot advanced his throttle and felt his Merlin engine surge with power that German fighters couldn't match, he benefited from years of chemical research. Every time an American fighter caught a fleeing German interceptor, the chase ended because laboratory work had been transformed into tactical advantage. The purple-dyed gasoline that flowed into Allied fuel tanks represented warfare transformed by industrial chemistry. It demonstrated that in modern conflict, the laboratory could be as decisive as the battlefield. That refining processes and anti-knock compounds could influence combat outcomes as surely as guns and bombs. That victory would belong not just to those who fought bravely, but to those whose industrial systems could transform crude oil into strategic dominance. 1 gallon, 1 sortie, 1 mission at a time. Now we return to May 1944, to Staff Sergeant Klaus Hartmann in his Messerschmitt Bf 109G, watching in disbelief as that American Mustang accelerated away from him with power that defied every calculation, every assumption, every documented performance parameter he'd studied. Hartmann survived the war. In interviews conducted decades later, he would learn the truth about what he'd encountered that day over Brandenburg. Not a new aircraft, not a tactical innovation, but a chemical advantage so profound that it had rendered obsolete everything the Luftwaffe thought they knew about American fighter capabilities. The P-51 Mustangs that flew over Berlin in early 1944 were remarkable aircraft, testament to brilliant aerodynamic design and engineering excellence. The P-51 Mustangs that flew over Berlin in early 1945 were mechanically identical. Same airframes, same engines, same propellers, but they were powered by fuel that made them faster, more powerful, and more effective. That difference, measured in octane numbers and performance ratings, in manifold pressure readings and airspeed indicators, was one of many differences that decided who would win the war for Europe's skies. And in that decision lay the fate of Nazi Germany. Victory expressed as purple liquid pumped into fuel tanks at English airfields. Burned in 12-cylinder Merlin engines at power settings that should have been impossible. Transformed into air supremacy through the systematic destruction of an enemy that couldn't match the chemistry, couldn't replicate the production, and couldn't overcome the industrial might of nations that had turned petroleum engineering into a weapon of war. One combat mission at a time,